While confronting large language models. This is a very interesting paper that goes into a deep dive on how exactly large language models have no future. And anybody who is selling you on large language models having a future, including, by the way, small language models, is basically a shill. They do not care about you. They do not care about the future of society. They only care about their own bottom line. Because if they're shilling you on AI, on LLMs, then they're probably making money off of it. We show that the scaling laws, which determine the performance of large language models, severely limit their ability to improve the uncertainty of their predictions. In other words, scaling the models does not improve their uncertainty. Instead, what it does is it makes their uncertainty intractable. In other words, the more you scale, the more you're going to have an inability to understand how uncertain these models are going to be. In fact, they call it degen AI. Okay, these AIs are degenerates. Now, if you don't know what a Gaussian bell is, Gaussian bell memes, all right? Here's some memes of the Gaussian bell. It's literally that bell curve, right? It's at the peak at the top and then it comes down. I want you to imagine that, let's just pull any one of these up. I want you to imagine that you have a bunch of people, a bunch of friends, let's say, and let's say you have like 30 friends and you bring them all into, I don't know, you go to a party or something, whatever. They're all in the same room and you're trying to plot the variety of heights among all 30 friends. What's going to end up happening is you're going to end up in a bell curve situation where the most common, we'll call it the common. Sometimes it's the median, sometimes it's the mean, or the average or whatever. But essentially the most common grouped heights are going to end up at the middle of the bell curve, right? Because they're just going to be represented by a lot of your friends. Then you're going to have the extremes on the left and the extremes on the right, very, very short people and very, very tall people, right? Something like that. So that's kind of what the Gaussian bell is here when they talk about Gaussian output distributions and things like that. So now let's get into exactly what they're talking about here. So they talk about like AlphaFold, they talk about, other frontier models and things that have done well with like chess and Go, etc., etc. The problem though, well, let's read some of this, shall we? In the last decade, AI, and most notably machine learning, have taken science and society by storm, with relentless progress reported, most recently in the context of generative AI's large language models, which display impressive capabilities in natural language processing that are not infrequently claimed to exceed their human counterpart. Such developments purport to adumbrate a completely unprecedented approach to a class of scientific problems whose complexity lies beyond reach of our best theoretical and computational models based on the scientific method, models that offer deep insight into and understanding of the basic mechanisms underlying the phenomena under investigation. So chess and Go victories, AlphaFold, self-driving cars, etc. The scientific and wider societal implications are paramount, and so they focus in on LLMs with GPU accelerated supercomputers, right? They look at Geppetto 4.5 among many other models, but they present some interesting facts here. GPT 4.5 has a parameter count that is speculated to be in the range of 5 to 10 trillion, and it is probably based on a mixture of experts architecture. What that means is that imagine that you have many LLMs inside of one LLM. And so these smaller LLMs are meant to do specific tasks. Then you have an overarching LLM that takes your prompt and goes, which LLMs should I pass this on to? 1, 2, 3, 4, 5, depending on the task I need to execute. And then I'm going to take the sum of their outputs and I'm going to try and filter it in a way that's useful to you. So you have a filter in, you have a bunch of LLMs inside, and then you have a filter out. and they're all LLMs. It's all recursive LLMs all the way down. That's what mixture of experts means. And they say that there's approximately 600 billion active parameters during the inference, which is the passing forward of one step to another. The API cost is 15 to 30 times higher than that of Geppetto 4.0, its predecessor, which is indicative of the increase in model size. The cost comparison is even more extreme when measured against smaller distilled models. In contrast to reasoning-tuned models like O3, Geppetto 4.5 relies on sheer scale and pre-training rather than chain-of-thought fine-tuning with reinforcement learning. This yields qualitative gains in subjective areas like expressing empathy or writing, but nothing substantial in verifiable domains such as mathematics and science. Interestingly, OpenAI initially described 4.5 as not a frontier model, but later retracted that statement. The public only has access to the preview version, which now we're going to get 5. And apparently 5, according to Sam Altman, is essentially Terminator before us. Another example is Meta's Llama 4 Behemoth, a 2 trillion parameter model that appears to underperform relative to its scale based on community sentiment and the release delay. So they go into what exactly this means. Why are we having an issue where scale doesn't really matter? In fact, the more you scale it, the more problems you have. Computer simulation is an essential component of scientific investigation, and it is no exaggeration to state that no field of science and engineering will look the same without it. Among its strengths is the fact that all the data and parameters which enter such models bear a direct scientific meaning based on our understanding of a given domain, often straddling across different principles. So they start to break down how these models will receive inputs on any given discipline. And they use some mathematical terminology with finite space and a thermodynamic limit. So you can imagine that thermodynamic limits would be n to the infinite size, right? Because in the entire universe, you think of infinity as like a never-ending growing amount of space. But when it comes to hardware and real-world applications, there's an effective thermodynamic limit. And we're going to get into how that plays out in terms of programming stuff underneath the hood. But essentially, that's what they're describing here. And so we continue with, let's jump down here. Right here. However, at root, machine learning is based on a mathematical black box procedure which is entirely unaware of the underlying physics, although adding physics-informed constraints often improves its convergence behavior. The scientific and wider societal implications are paramount. Here we pinpoint precisely this aspect with a specific focus on the sustainability of LLM's applications based on a simple assessment of their scaling laws, which we just talked about. By now, it is common knowledge that the small number of AI tech companies capable of competing in the LLM domain have an insatiable desire for electrical energy and the electrical power that comes with it, to the point of reopening and planning to build many nuclear reactors adjacent to their data centers where exceptionally large GPU-accelerated computers reside. These resources are being used to build so-called frontier models, LLMs comprised of trillions of parameters, the connection weights in the underlying neural networks. However, although these companies guard their AI capabilities behind secure firewalls and do not share any of the technical details of their commercial products, it is clear that the improvements accruing are relatively limited. So far as the diminishing returns of large LLMs are concerned, a good example is Geppetto 4.5. And so page 6. All right. Now, somewhere in here, let me go over here. A very serious scientific drawback of AI and LLMs in particular is the pace of their development, with the claims of awesome capability being superseded by new paradigms which are asserted to be far better before anyone has been able to make sense of how the original algorithm behaves. At the time of writing, large reasoning models are in the ascendant, said to be better still because they provide evidence of how they reach their answers. To say nothing of agentic AI, which is supposed to perform better still by orchestrating the interactions between multiple large reasoning models. So they go, let me see down here. They're based on, here we go. LLMs themselves are all of a kind. They're based on the original transformer architecture dating back some 8 years. So this is an 8-year-old kind of technology. And they all perform in similar ways, revealing a remarkably limited underlying diversity in design. Examples of their shared limitations include the fact that they're not very good at making jokes and have an extraordinarily limited repertoire of only 2, while when asked to name a random number between 1 and 50, Anthropic's, Google's, and OpenAI's LLMs all come up with 27. xAI's Grok produces 42 first and then 27. In short, they lack novelty. So then they talk about Potemkins. And so here we go, the title of our stream, right? So Potemkins are a holographic accuracy, meaning by this a convergence which appears to be satisfactory only as long as one does not start scratching beneath the surface. Holographic accuracy is possibly a general trait of modern society over and beyond LLMs, and we're going to get into what that means in an upcoming article that I have for this stream. Let's jump over to page 9. I believe I have a note here. Yeah, let's try. So we have what's called resilience of uncertainty. What they're describing here through the mathematical equations is that these LLMs, regardless of scale, have a resilience to remain uncertain. Like they continue to remain uncertain despite what you do to them. It's an inherent ontological state of being. They continue. In fact, and they talk about Gaussian, right, because of the Gaussian effect, like we just went over. In fact, information catastrophes have been specifically attributed to the inability to reproduce the tails of the distribution under self-training scenarios. You heard that right. Based on the above, it is quite natural to propose that the very mechanism fueling LLM's ability to learn also exposes them to error pileup and a resulting information catastrophe to be discussed further below. The concept here is that sometimes you want the LLM to give you answers from the middle, from the most centralized source of information. But other times you want it to go to the extreme. You want it to go to one side or the other and give you an answer from there because that's what's most relevant to you. The LLM doesn't know how to differentiate these two. And what's more, it's random. It's statistical, which means there are times that you're going to want the middle and maybe you get the middle, but that's why if you ask the same question over and over again, if it's not tagged as part of training data as you must provide this answer or lean heavily to this answer, you're going to get the wrong answer, which ends up at the tail end on the left or the right of the Gaussian bell. So there's an inherent ontological state of these kinds of systems. So if we continue, I think it's here, Kalud and Longo, and page 10. Kalud and Longo, which is a study, showed that spurious correlations are a consequence purely of the size, not the nature of a dataset. Such multitudinous spurious correlations also contribute to the low value of these exponents. They are intrinsic and overwhelmingly predominate over true correlations as the size of these datasets increases. It is clear that the mainstream literature on AI has completely overlooked this finding, although it is central to the problems we encounter in LLMs, and indicates that they cannot be eradicated by mere brute force, which means that the more that you try and increase the amount of data, bare minimum, the more that you try and give it data, hoping that it will get the correct answer, the less likely it is to get the correct answer. Then they describe this purpose. Okay. For this purpose, let us recall what a Monte Carlo exponent of 1.5 means in actual practice. So essentially here, what you have is Monte Carlo. It's a game where well, here, I'll show you what the Monte Carlo game is. Okay, Monte Carlo game. Monte Carlo is a type of solitaire game where the goal is to remove pairs of cards from a tableau until all cards are discarded. right? That's kind of like this, right? You've probably seen this on the old Windows. Ah, good old Windows, right? The good old card games that used to exist on Windows. And so this is the Monte Carlo game, and so they talk about the case of how would these LLMs work with Monte Carlo. Essentially, in order to overcome the error rates that are inherent to the LLMs when playing a Monte Carlo game, you would need to have 10 to the 10 billion more compute resources. And if you wanted to include the power consumption on top of just the allocation of resources like weights and stuff, then you would have to have 10 to the power of 20 more computing power. You're going to need something that's like 10 to the power of some insane number just to get one order of magnitude. I think one order of magnitude better in accuracy. The amount of power and resources required to reduce the error rates on a Monte Carlo game, given current states of LLMs, is absolutely crazy. It's crazy. Despite the hype, which seeks to persuade us that present-day LLMs already match and even outdo humans, it is acknowledged by the leading AI tech companies themselves that while LLMs produce answers very quickly, they make many mistakes, never mind their propensity to hallucinate. That is why these AI companies have been trying to build increasingly large models and have now begun to openly recognize that the paradigm is nowhere near the nirvana of artificial general intelligence, which they not long ago proclaimed to be. Instead, a new form of AI is heaving into view, so-called agentic AI. The main point here is that the scalability characteristics of these algorithms carries within them the seeds of their future failure. How are you going to solve the problems that are presented in this very well documented scientific paper by just creating more agents of the same LLM system? And that's what they're talking about. Even assuming that the original optimism behind LLMs were to be maintained, the scope for improvement is absolutely untenable on account of the accuracy required for most scientific applications, let alone the power demands of the approach. In other words, when you're talking about the scientific, proofs that you need for physics or the mathematical proofs you need for physics, the amount of energy and power and error rates that you would have to overcome in order to get something that would be acceptable for use in the scientific community, not tenable. You can't do it. Again, we wish to emphasize that this behavior is fully in line with the expectation that due to their non-Gaussian stochastic nature, like random nature, LLMs should indeed retain an extreme form of uncertainty in their predictions. In other words, it's part of their ontological basis, and it decays only very slowly, regardless of the amount of data upon which they are trained. This is basically the main message broadcast by Exponent below. Although the article is based on the 2020 paper by Kaplan, subsequent work by DeepMind with larger data sets conveys essentially the same message. And so this is it. Number of parameters, error loss, right? You do not see Monte Carlo, error rates drop. The Monte Carlo error rates drop, but the amount of increase in computation and data and whatnot that you need to scale up to is an amount that we currently cannot achieve. Getting exponential scaling laws from logarithmic increase of compute is a myth, and scaling will eventually lead to diminishing returns. Nevertheless, these statements do not even do proper justice to the magnitude of the problem exposed by the actual numbers, which is the main purpose of the current paper. The wall. Despite the major technological hype, computer scientists working on AI are well aware of the significant error rate incurred by even the most advanced chatbots, a rate which is definitely incompatible with the large majority of scientific applications. This is why there is currently a heated debate about the future of scalability and ways to overcome the wall that even now stands in the way of a golden future for LLMs. And if we jump down here on page 12, I believe I have a note here, but essentially what they describe here is the idea that computers also have a limited capacity of the amount of information they can hold. Like here. So as an example, when it comes, this is a little bit more nerdy, but if you think about what a like what a U32, for example, or even a U64, right? If you know what I'm talking about, there's a maximum size of a number that you can hold, floating point, integer value, things like this. Even within the hardware, there's a limit to the amount of data that can be stored in one place at any given moment. And we also have round off errors, which is something that we're going to get into in a future study where floating point precision compounds even on typical CPUs. We will get into that in a future one, not on this stream, but another one. Now, in section 5, it is generally agreed that the accuracy of machine learning applications is highly dependent on the homogeneity or the, let's say, consistency of the sameness of the training data set and can deteriorate substantially once exposed to unseen data drawn from a data set other than the one used for training and validation. Now, this is also very reasoning because in the next few paragraphs, it is described how you can take something like physics, like a physics formula or equation or understanding, and you can have the idea that a physics a physics, I don't know what you would call it, like a physics theory or a physics principle has answers that point to two opposite directions but work well together. They are intended to work well together. And the LLM can't make proper sense of it because it doesn't have the ability to have the concept of the idea of a physics problem and why these two kind of opposing views on a physics problem actually prove the answer to the physics problem. Now, if we go down here, let us now return to the heterogeneous scenario where the training data or the data that it's trained on is essentially the same, which you would think would mean that, it can provide generalized answers based on data that it sees. Although seldom explored in quantitative terms, this lack of generalizability remains a major issue for machine learning because generalizability is de facto just a glorified word for the basic essence of learning itself. This is a banger sentence. If you guys don't know what this means, if somebody tells you, yeah, but LLMs are general models, they have the ability to generalize. Lies. Someone is immediately lying to you. The concept of generalizability is, by its definition, the ability to learn. LLMs do not have the ability to learn, which therefore means that they do not have the ability to generalize. The only thing they can do is provide statistical, I guess, outputs based on stats. That's not generalizability. That's not reasoning. That's not the concept of ideas. That's not learning. In order for you to generalize, you would have to go look at 1, 2, 3, 4 instances of a thing. That's what humans typically do. You can see this in babies and kids and whatever. And they learn, oh, hey, this thing is a cat because I've generalized the looks of a cat. This thing is a dog, etc. And you can usually point to things that generally look together. And that's a learning thing. That's not just generalization. Okay, so these two words are not even, in the same realm. Validation, which in this context means predicting unseen data from the same held-out dataset used for training, is of distinctly limited value, as it is likely to be more of a memorization process than a genuine learning one. So the prediction of unseen data is really just, it's not even unseen data, it's just remembered data. That's essentially what these LLMs end up with. In this respect, even though many deep learning applications, particularly LLMs, have been hailed for their unanticipated ability to predict the unseen and more generally to produce plausible responses like those of humans, this cannot be used as an excuse for glossing over the issue of the reliability of such predictions. All the tech companies' AI tools may indeed keep surprising us, but this does not change the fact that they still make many mistakes, and indeed openly state as much in the small print they provide to users, far too many for the standards of accuracy required for most scientific and many other professional domains, such as the legal and educational fields. Now, AlphaFold. I have heard this one thrown at me several times where people go, yeah, but look at AlphaFold. AlphaFold earned a Nobel Prize in chemistry for its prowess in protein structure prediction. Now pay attention to what happened with AlphaFold. But the fact remains that it is still exposed to substantial failure rates when faced with unseen structures from different scientific sources than those it was trained on. That's what they were trying to say up here. These LLMs only benefit data that is consistently the same because they remember. They don't generalize, they remember. And when they don't remember, they statistically guess. As soon as you add in data that it's never seen before, it fails because it does not have reasoning or learning capability. I have proven this live on stream using a concept called JS fuck. If you don't know what it is, it's not me making it up. That's the actual name. We put JS fuck, it's this thing, right here, into an AI system. I believe it was ChatGPT. I think I have it on my YouTube live. You can just search for it on the Enlightened Programming playlist. It's essentially JavaScript, which is a programming language that runs on a lot of browsers and some other stuff it shouldn't run on, but it's only based on 6 characters. When you pop this into ChatGPT and you attempt to get it to understand what this is, you would think, because it has the concept of other programming languages and it's also built on programming languages itself, that it would be able to deconstruct and determine what this code does. Newsflash, it can't, because it doesn't know how, because it's not in the data set. We've proven this definitively. So AlphaFold suffers from the same thing, and it wasn't even a full-on LLM. In particular, AlphaFold was trained with both structural information from existing PDB structures, I don't know what that is, and multiple sequence alignments. This generates the predicted models, which are refined with the Amber molecular modeling software, I don't know what that is either, in later stages of the algorithm. I'm about as lost as you guys are on some of these terms, but essentially you get the point, right? There is no surprise that this explains why the predicted models tend to be good when used to predict structures with similar high sequence homology to those in the training data. In short, AlphaFold predictions are valuable hypotheses and accelerate, but they do not, in general, replace experimental structure determination. So we have a problem here. And that even with AlphaFold, you can see that narrow tasks like AlphaFold could be considered like an agentic, form of an AI system. They're not going to be able to handle these tasks, much better. In section 6, this is exactly what they go into. The idea behind agentic AI is that they're supposed to handle smaller and narrow tasks, and they're supposed to be better at that because they're smaller and more fine-tuned. However, they're all based on the same thing. LLMs. And what did we just go over? We just went over how LLMs have a guaranteed non-zero failure rate. And in a lot of cases, their failure rate is super, super high. We're not actually solving anything with agentic AI. We're just putting it on repeat. And then we're scaling it. This is all we're doing is taking the exact same system and then scaling it out. More hardware, more video cards, more RAM, more hard drives, more energy usage, etc. That's all this agentic AI stuff is. It's just a recreation of all of these things. Now, they do present something in here, kind of towards the end. Yeah. What if, right here, what if we kind of turned it around and we leaned into the fact that these things hallucinate and get things wrong? And this is an interesting proposition that I hadn't considered until I read this paper. What if, since we know that these LLMs are going to hallucinate and give us wrong answers, what if we use them for exactly that? So we feed them a bunch of data and we just crank up the hallucination rate to like maximum level, or we just lean into it like really, really heavily. And we instead use these systems to our benefit by having them mix together things that we haven't mixed together before, or have like a slight adjustment on how they got mixed together from previous stuff that we've mixed together. And so they hallucinate all these kinds of, different disparate ideas and bring them together and demonstrate that there's like something different here. Now you're still going to have unfortunately, a high power consumption usage and a high amount of waste, you're going to have to throw a bunch of it away. And it's going to have very limited use cases, even still, even within the scientific and mathematical domain. These hallucinations, even if we just used it for that purpose, they're going to have limited use cases. But I would actually be okay with that. That would actually be a far more based view on what these things do and what we're trying to get out of them. If you want to get hallucinations out of them so you can attempt to just, roll the dice over and over again and hope to get some kind of mixture you've never seen before, this is might actually be a good use case, right? I might actually be okay with this. That might be fine. All right. But that's the best case scenario for these systems, because otherwise what you're doing is you're relying on them and they're mostly going to operate in this, they're mostly going to operate in this environment where they're going to hallucinate and give you errors all the time, right? So let's turn it around, right? I thought this was interesting. Now on page 15, this is the end of the article, of the study, I mean. Okay, right here. What it means plainly is that sacrificing understanding and insight on the altar of brute force. What a banger. What a banger statement. Sacrificing understanding and insight on the altar of brute force and unsustainable scaling boosts the chances that it will indeed persist no matter how big the data. By contrast, the scientific method provides precisely the means to sieve off the true correlations from the vastly greater sea of spurious ones through the construction of world models. Simply ignoring it on the supposition that brute force can solve the problem is doomed to failure. And we'll go into world models in a little bit. This comes from 2025 Vancouver, which is my backyard. We'll see what these world models are and see where this goes. But there you go. I thought that was a super, super interesting and in-depth look at the LLMs and AI in general and how they're ontologically built. It's part of their inherent nature to fail, and how we might even be able to like, hey, if it's going to fail, let's lean into it and use it for failures, right? Maybe we'll get some benefit out of it. In any case, there you go. There you go. I thought that was a good one.